That's time. Well, good afternoon, welcome, and please tell me what you think. By the way, the answers to questions for discussion one assignment is on the blackboard. This is one of the questions you've answered before, so still it's nice to review. How do we subtract vectors? Yeah. Sorry? For the response where? Tools. Log in. $34, $64, $94. So as we know now, in physics, all questions based on certain definitions. Here, first, we would have to recall a definition of subtraction. We know how to add vectors, right? Tail to a head rule, that's it. So, to subtract two vectors, we have, yes? The channel is supposed to be 21. Let me check. I guess when it's collecting, but it's 21. All right. So the definition of addition is definition of addition is tail to a head rule. The definition of subtraction, we should rewrite it in terms of addition. So that's what a subtraction is. Numbers, vectors, doesn't matter. It's adding the negative or the opposite, number or a vector. Now we have to use a definition of the opposite vector, yes, what it is. And the opposite means opposite. It's an arrow. It must have exactly the same magnitude, but should have opposite direction. So it's anti-parallel to its original vector, right? So this is literally this. And now we know what to do, because we know how to add vectors. A plus opposite to B or negative B. The resultant if we look at the resultant, the most appropriate answer should be number 1, right? So let's see. Yep. So nothing to think about anymore. You know probably everything about vectors. Try to recreate your train of thoughts, because something went not the way it's supposed to, and the best way to avoid making the same mistake in the future is trying to recreate, your reasoning and see what might have gone wrong. That's it. Now, no. I want to save this picture. And feel free to ask any question. Oh, I got a sound today. Huh? All right. Moving on. This is the answer. Yeah. Much better drawing than mine, so that's why I include it. Now, from our experience, we know pretty well that when we're adding or subtracting vectors, we always end up with some kind of a triangle. If it's a right-hand triangle, that's kind of easy situation. We know what to do, but it's not. It doesn't have to be a right-hand triangle every time. So what do? We have 2 options. Number 1, if you're confident with your geometry skills, you always can use 2 additional theorems. This is a sine theorem, this is a cosine theorem. You don't have to. No, it's up to you. Because you can always actually make a right triangle. You just have to draw a perpendicular. So, like this, for example. And now you have 2 right triangles. And what do we know about right triangles? Yes, where else? There's one word which answers this question, yes? Everything, exactly. So, you know everything about these 2 right triangles, which automatically means you know everything about any kind of a triangle. In the future, we're going to use a situation like that pretty soon when we talk about forces. So, let's go back to motion. We've spent a lot of time talking about vectors because if we know how to use position vectors, we know how to use any kind of vectors: velocity, acceleration, force. Is temperature a vector? No, so just a number. Anyway, but let's go back to talking about motion. This is a picture from the past, all the known definitions, so we can make a next step in our reasoning. We know everything takes time, motion takes time. So you can ask a question, okay, how fast did it happen? Or how fast is it moving? In physics, there's always the same way to answer this question. The motion is the change in the position. So how fast does position change? To answer that question, we need to calculate the rate of change of something related to the position. Well, if it's a temperature changing, to figure out how fast does it change, we should calculate the rate of change of temperature. If we're losing money and we want to know how fast, we should calculate the rate of change of losing money. So how fast always means the rate of change of whatever changes. We have several variables related to motion. One is a displacement. It's a vector, right? Another is distance. So we can ask, how fast does displacement change? How fast does distance change? And to answer this question, we introduce new definitions. That one on the left. That's what we call the average velocity. This symbol represents the displacement. If displacement takes a certain amount of time, that displacement divided by that amount of time, that's what we call average velocity, a definition. This is what we call instantaneous velocity. Sometimes we want to ask, how fast is it moving here and now, right? So not over some period of time in the past. No, here and now. In that case, what do? We look at the instantaneous displacement. So if I'm here right now and I'm moving, in a fraction of a second, I'm slightly moved. So if I take a very, very small time interval, my two consecutive positions will be very, very close to each other. So, and if I take that very, very tiny displacement and I divide by very, very tiny time, that's what we call instantaneous velocity. That's it. So if a fly is flying, this red arrow represents the displacement. It takes some certain time. A displacement is a vector. Time is a number. So if I take a vector and I multiply by a number or I divide by a number, I still have a vector. That vector will have a different magnitude, but what about the direction? So this, again, what we call average velocity. What's supposed to be the direction of this vector? Please, anyone. How would you describe the direction of the average velocity?
Measure it in degrees.
That would be the next step. We would have to measure some angles, of course, but if we want just describe a direction, we can compare with other directions which we can see, you know? Yes? Well, east would mean directly horizontally to the right. I wouldn't say that would be correct direction. I think that's a good place to ask a question. So I'm going to give you several choices, natural choices. 1, 2, 3, 4, 5, 6, 7, 8. Which of these 8 arrows do you think would describe the direction of the average velocity? Or at least the best description of the average velocity. And again, remember, what you're doing here, oops. What you're doing here is this. You're having a vector, and, well, you're multiplying by a number like that. Yeah. 1 over delta t. That's a coefficient. So this coefficient, that's a number. That's how we measure time. We start from 0, and it goes ahead, and eventually it could have been an hour or days or decades. We don't know. We do know that this number, well, as any number, could have been positive, 0, or negative, but only one of these 3 options is correct for time. And if we combine these 2 pieces of information together, did I start collecting? Yes, I did. It's still, okay, 82. It's still kind of strange because when I checked last time, we had 109 students on the roster. So, and think, what would you have answered if you actually had an arrow like that, the black one, and you would have to multiply that arrow by, let's say, 2.5, what kind of an arrow you would get in the end, you know? Let's see. 88. Oh, 2 8. Good. 2. I would answer 2 as well. Because again, time, change in time is never negative, it's positive. So if you have a vector and you multiply and dividing by a positive number, you get a vector which has a different magnitude, but it has the same direction as the original vector. So to describe this situation in words, we should say the average velocity is just a vector which is parallel to the total displacement, parallel. It points in the same direction. We don't have to use any actual degrees at this point. Later, if we need to describe that direction mathematically, we would have to introduce the x direction, and we would have to measure or calculate this angle, directional angle, but that would be a later step. All right. Instantaneous velocity. Same flies, start, beginning. This red arrow represents what? Total displacement, net displacement, complete displacement, doesn't matter. But we can ask, okay, here and now, what was the instantaneous velocity of that fly? Well, according to this definition, we should consider 2 consecutive instances, 2 consecutive positions, which are very, very close to each other. So next position would be here. So I would have to kind of make an enlargement. Yeah. Position number 1, position number 2. So that should be my instantaneous displacement. And now we know if we take this arrow and we divide it by time, doesn't matter if it's a huge amount of time or tiny amount of time, we still should have an arrow which points in the same direction. So my instantaneous displacement points like this. So if I want to draw my instantaneous velocity, that should be a vector like this. I don't know how long or how short that vector is without using any numbers, but I know for sure it should point in the direction of the instantaneous displacement. And if you look closely, this arrow, the blue one, touches the trajectory only once, only at one point, yeah, ideally. So how do we call a line like that? Tangent, yeah. So instantaneous velocity, always tangent to the trajectory. Here, it points like this, it points like this, it points like that. So in general, when an object is moving in a complicated manner, instantaneous velocity constantly changes. Another thing to remember, there is difference between distance and displacement. So far, we've characterized the change of the displacement. But in the same way, we can characterize how fast distance changes. So we can introduce 2 more definitions. Number 1, the average speed. The average speed is a number. That's not a vector anymore. It's a number, which we get as a result of division. The total distance traveled divided by the time of traveling, the average speed. Here, that's what we call instantaneous speed. See how many vertical lines do we have here? They have slightly different meaning. This line tells us that we should consider two very close instances in time. So this is the instantaneous velocity, and these two vertical bars mean magnitude or absolute value. So instantaneous speed, by definition, is just magnitude of instantaneous velocity. So here, to calculate average speed, first we need to calculate or measure total distance traveled. Then we need to measure time, divide two numbers, done. Here, to calculate or measure instantaneous speed, we need to calculate or measure instantaneous velocity first, and then take its absolute value, take its magnitude. All right, I'm going to take a break. This is for you. So you should solve, and I will ask one of these questions. I'm not going to ask all of them, A, B, and C. Only one. I'm not sure yet which question will I ask. So I'm retiring for 5 minutes. As you know, when you solve a problem, either you know what to do, and in that case, it's not actually a problem. Yeah, it's a task. Or you're not sure what to do. In that case, you should try something, or you should ask a question. Raise your hand and ask a question. Yes?
So L, the variable L that you have, is the total distance traveled?
Yes, total distance traveled.
Right?
Yes.
Okay.
No comments. Maybe I should move it down a little. Again, the first step is reading and imagining. The problem-solving strategy, as we know, is always the same. We read, we imagine, and we draw a picture. Then we look at it. Then we start thinking about definitions which we should use. Then we use those definitions. I'm not collecting any responses. You see, this is a triangle. So until it becomes a square, I'm not collecting anything.
Sorry, I was confused about, I didn't get a chance to copy down the average and instantaneous speed.
So this is definitions for average speed and instantaneous speed. The average speed is distance divided by time, total distance divided by total time. And the average velocity is total displacement divided by total time. And don't worry about the instantaneous stuff yet. Yeah, let's just solve for average speed and average velocity. We'll discuss the last part later. So at this point, concentrate please on average speed, which is supposed to be equal to total distance over total time, and average velocity, which is supposed to be equal to total displacement over total time. And you don't have to use meters, seconds. It says use kilometers per hour. 2 hours, 80 kilometers, 60 kilometers. That's it. And I will ask a question about the average velocity. So natural set of answers looks like this. 1 for 10 kilometers per hour. 2 for 20 kilometers per hour. 3 or 30 kilometers per hour. You see the pattern, right? Etc. And we always reserve 0 for none of the above, right? The good news, it seems like I've recovered my speech ability. Knock on wood. The bad news is I don't know, can't think of anything. So they don't always come in pairs, right? So if you have done your work and you're confident, you're pressing. If you're still working, keep working. I want to start. So that's what I'm doing when I'm imagining things. Okay, now I'm projecting it to the paper. I'm not really good at drawing. It has to be a completely straight line. Yeah, it's a vector. It cannot be bent. So ignore. No. Plus, I don't have a ruler handy. So 80 and 60. What is the total distance traveled? Exactly. So if I want to calculate the average speed, according to the definition, I have to calculate the total distance, well, 80 plus 60, and divided by the total time. It took 2 hours. So that gives us, can't hear you. Someone should say very loudly a number. 70, of course. So no tricks. Now, do we get any 90 today, at least? Now, average velocity. If we are looking for average velocity, we must start from a definition for average velocity. Average velocity is supposed to be equal to the total displacement. Well, probably not good using the same over total time. Now, now we have to apply the next definition. It has to be a vector like that. Now we have to look at it and recognize the shape of this figure, and we have to name it. And because we name it correctly, right, and triangle, and we know everything about it, we can apply. What's the name of that theorem? And the result is? So what's the magnitude of this displacement? 100. And so now we go to a tricky part again, verbal assumptions. A question like that, very commonly used for homework problems and exam problems, lab situations. We want to enter a number. Yeah. So when the question is, what was average velocity? The answer should be the number and then direction. So the number for the magnitude of average velocity is equal to 100 over 250 kilometers per hour. The direction, well, to describe the direction again, depending on the situation, we might be told how to measure angle. It could have been said, measure from west direction. In that case, that should be the number. Otherwise, we always can assume that there is a positive x direction and a directional angle should be measured like this, counterclockwise. So that's it. Can we calculate those angles? Of course. For example, this angle, let's call it psi, should be equal to what? If we know all sides, we can use any trig function. We can use sine, we can use cosine, we can use tangent, doesn't matter. I usually use tangent. So tangent of psi will be equal to 60 over 80. Three-quarters or 0.75. So how do we get the angle itself? It's supposed to be the inverse tangent of 0.75. So you should take the calculator. Normally you would press second function button, tangent, 0.75 equals, and that gives you about 37 degrees. So this is an important moment. People usually forget that 3-4-5 triangle and 30-60-90 triangle are completely different triangles. This is a 3-4-5 triangle. The angles inside kind of weird, 37, 53. So you cannot assume that if you look at the 3-4-5 triangles, you cannot assume it's 30-60-90 triangle. No, it doesn't work. 37, okay. Any questions? Let's see what you said. Perfect. All right. And again, if you have any questions, please raise your hand and ask a question. At this point, we are moving on. I'm not sure what's happening with this system. I'm not going to ask this question. Yes?
When you write down the angle, would you write it down as 180 plus 37 or just 30?
That depends on what, well, let's say this is a problem you have to solve in a WebAssign. WebAssign usually tells you how the angle is supposed to be measured. It's not always from positive x direction counterclockwise. So wherever you're told to do, you have to do. If nothing said, I would add 180. That's my natural assumption. I always follow the definitions. But if it says, at what angle do it to west? Yeah, that would be 37. What do you think? Anybody, please? You're driving? Or flying a plane and you're looking at your dashboard. What do you think do you measure? Yes?
Instantaneous speed.
Absolutely. Not instantaneous velocity, because velocity also has a direction. Not average. It's happening here and now. You read numbers, and that's your instantaneous speed. If you're slowing down, it decreases. If you're speeding up, it increases. If you keep your pace constant, it stays the same. Like in this question. Part C. If you kept your pace constant, what did you keep constant? Velocity or speed? Speed, exactly. Because velocity actually changed. At first, velocity was directed west, and then south. So your speed had been constant over the whole trip. And constant speed means you were, if you had a pedometer, yeah, that would give you the same number, which was what? 70. Right. But the question about velocity, well, in that case, you should have said, okay, on your first part of the trip, your velocity was equal to 70 kilometers per hour west. You have to add the direction. And then on your second part of the trip, your velocity was equal to 70 kilometers per hour south or down. You know. So when you talk about velocity, we're adding an additional information, direction, one way or another. I'm going to skip this question. I'm going to skip this question. I'm going to go to this. What do we do if the velocity changes? If the velocity changes and we want to know how, we should calculate the rate of change of velocity, right? So for the rate of change of velocity, again, I'm not collecting your answers. Anybody, please tell me, which equation would you use for the rate of change of velocity, let's say average, on average? That's what we should call average acceleration. Number 1, number 2, number 3, number 4, what do you think? Again, we use our, well, intuition in this situation. Yeah. Rate of change of position was final position minus initial position divided by time. And we called it velocity. Now, rate of change of velocity. Of course, it's exactly the same pattern. If we want to calculate rate of change of velocity, we should subtract initial from final divided by total time. That gives average acceleration. If we consider two consecutive instances which are very close to each other, that would give us instantaneous acceleration. And technically, we could calculate the rate of change of acceleration, then the rate of change of acceleration, and the rate of change of acceleration, et cetera, et cetera. But we don't need to do that because, lucky us, in physics, everything important stops at acceleration. So we need to know how to deal with three important variables: position, velocity, acceleration. This is an official definition with the average acceleration, yeah, final velocity minus initial velocity. But we must remember, we use vectors. Initial velocity is a vector. Final velocity is a vector. We subtract two vectors, we divide by time, and that gives acceleration. In this question, I want to ask you, if we know the acceleration, and if we know the initial velocity, can you tell what will be happening to the speed? You know? So my question is, you have 4 pictures here. Which picture or pictures describe the car which speeding up? Speeding up. Which, if you look at the speedometer, the numbers go up. Only A, press 1, only B, press 2, only C, press 3, only 4, only D, press 4. And there are combinations. If it's A and B, 5, C and D, 6, A and D, 7, B and C, 8. Well, 9 or 0 would mean something else. Okay? Speeding up versus slowing down. Each vector A represents instantaneous acceleration here now. each velocity, each vector v represents instantaneous velocity here now. It's like a snapshot. But if we keep taping, if we keep capturing, what would we see? Would be speeding up, slowing down? Yes? That's a very good question, but at this point, it has nothing to do to what's happening. That would be the next question. How should we describe this mathematically? Because each vector has components. Components could be positive, negative. We don't need to do that if we know how to use vectors, how to add and subtract vectors. Remember, I'm going to give you a hint. Oh, 91, great, I can stop. But I won't. Okay, I'm going to give you a hint. That's the acceleration, velocity final minus initial, or number one, over time interval. Doesn't matter, average, instantaneous. We want to know what's happening to velocity. So the best way to figure it out is to solve it for velocity. So first we can multiply acceleration by time. We know it's just some positive number. And that should be equal to this difference, final minus initial. Now, if we want to solve it for the final velocity, we just have to add, or bring it over the additional velocity, the initial velocity. And that gives us this expression, which is much more convenient for problem-solving purposes. So if you have initial velocity and your acceleration is given, that's what acceleration does. It changes velocity. If the acceleration is 0, the velocity doesn't change, stays the same. If it's not 0, what's happening? Well, let's take a look at the picture D. Okay, D. So that's, oops. That's what we're trying to do. That's supposed to be equal to the initial velocity, which is an arrow pointing to the left, picture D, plus the acceleration, which is an arrow pointing to the left, multiplied by some number. So you are adding two vectors which point in the same direction. So the resultant will be an arrow which, and you have to finish, shorter, equal, or longer than initial velocity. So what do you think? Longer. Of course, you are adding. You had this, and you're adding some more. So this is your V2. So how do we call a case like that? Speeding up or slowing down? Speeding up. The magnitude of velocity, which is speed, increases. So this is a case of speeding up. And we can analyze in a similar way all other situations. That's the purpose of this exercise, using our understanding of, well, vectors. For example, very quickly. Okay. C, what do we have? V2 supposed to be equal to V1 plus acceleration times time. The resultant, again, we only have three options: shorter, equal, or longer. Shorter, yeah, that's what we're doing. V1, then a little bit back. So this is our V2. How do we call this? Slowing down. It slows down. A, speeding up. B, slowing down. We can make a very simple conclusion. If you have velocity and acceleration parallel to each other, pointing in the same direction, that means speeding up. If you have velocity and acceleration opposite to each other, anti-parallel, that means slowing down. In terms of numbers, now, you are absolutely right. Every variable, almost except time, is a vector. So relative to our x direction, for example, this arrow has a component, we call it Vx, which is positive. And this arrow, that's case B, I think, has a component, yeah, relative to that axis, which is negative. If you want to write the equation using components, V2x should be equal to V1x plus AX times delta t. Literally, nothing changed. We just dropped all little arrows above this variable, that variable, this variable, and we have it replaced with the letter x, literally. But again, if we look at the numbers, now we need to remember, okay, this is a positive number, but the x component of acceleration actually is a negative number. We can write it like this. It equals to minus times magnitude. So it's negative something. You are subtracting. Of course, that gives you a number which is less than this. But I think that my pictorial method is simpler. It's up to you what you want to use. So these are answers. Now, I ran out of time. Of course, the easiest, okay, 7. I agree. The easiest way to describe, the easiest motion, the easiest kind of motion is the one-dimensional motion. In general, a position vector might have 3 components. We call them x, y, z. But if it's a one-dimensional motion, we only need one component, x, and we call it x-coordinate. And there are many cases of one-dimensional motion. The case number 1. Time is running. The position doesn't change. How do we call it? Rest. The object is at rest. Now, the object was at rest, and now it was moving away from the origin, relatively, steady motion, and then at rest again. That's what we call a linear motion here with constant velocity. What if we do something like this? We know that when it was sliding down the ramp, it was actually speeding up. You see, that was the time interval, about a couple of seconds, even less. But the motion, the cart of this motion was different from the previous experiment. Speeding up reflects in some curvature here. So this is how position of this cart changes in time. This is a graph for the position as a function of time. And if you see something like that, it's actually a parabola. That means your velocity changes. And we actually can do some things about it. but not today. You will. This is all you need to know for the lab. The current lab is very similar to this. And I'll see you on Wednesday. Thank you very much.
Professor, so I have lab today at 3:30 to 6:30, but the university just sent out an email closing campuses at 5. So would we still have lab up until 5? Or how would that work?
So the evening lab is canceled, that's for sure.
We just got an email saying all university activities after 5 p.m. on campus
Yes,
today.
yes, I know. Right? So now I'm thinking. So you, so 3:30 to 5.
Yeah, lab from 3:30 to
3,
6.
so you're missing 1 hour. That means
Or an hour and a half.
I'm going to cancel this lab. Yeah, maybe I'm just cancel. Well, so I'm going to send an email.
Okay.
No labs today.
Okay.
Everybody, no labs today and tomorrow. The email just has been sent, so, and I will figure out what we're going to do.
Okay.
Oh, thank you.
Thank you.
And I will send in a confirmation email like in 5-10 minutes.
Oh, okay, sorry. So will the email state what lab? Like, I mean, do we have to ask our TF to join
No,
a different
that's
lab?
it.
Yeah, I know, but to get into, because I don't want to lose credit for this.
Nobody, if it's a snow, nobody loses credit for anything, no matter what happens.
Well, I'm referring to the labs on Wednesday.
I actually expect Wednesday lab probably will be canceled as well. So we only have one section. So probably I'm just going to cancel the whole lab number 1, just kill it. That's it. That's the easiest solution. But I'm going to send an email, okay? So don't worry.
Thank you so much.
I emailed earlier about missing the I don't believe so.
Well, anyway,
I don't know. Yes.
so it tells you that you don't even have to make up missing 2 discussions and 2 labs.
Okay.
So you're not losing any points on that.
Okay. Yeah, I
If you
can
want to just
probably get
practice, you can go online on a blackboard. You can find
And it'll
that
be-
assignment. Well, it's already done, but you can kind of close your eyes and
Okay.
try to redo it again.
Okay, great. Thank you.
I'm still having a problem with my clicker. It says my number wasn't on the email you sent out earlier, but I have this, my clicker's a little different, it has a screen. I need it for another class. But
It should work.
it should work, yeah, I called Turning
Let me
Technology.
check. Just in a minute.
Okay.
First of all, first I need to check if your clicker and the system actually talk to each other.
Right.
And do that, I just do this. Who left me this? The person who left me this is supposed to pick it up again. Please press your button on your clicker.
It says not an option retry.
Can I see it? It's shutting down, so as long as it's black, you can.
But you said that's not an option retry.
Did you set up the channel?
Yep, it finds the channel too. You could
No, because that's when you close it.
Yeah, 5, but mine's up to 30.
Okay. I'll call the company and see what they say, because I've never seen that response before either, so. Thank you, Professor.
I have a 3:30 lab today, so I was just wondering if you still have it.
No labs today. Okay. Just a quick question with regards to scheduling makeup labs. Is that going to happen, or are we?
I don't know yet.
Okay. All right. Thank you.
The Rouse Lab, the fourth level closed at 5 p.m. Are you our lab professor for chemistry? Are you our lab?
I'm leaving.
I know you're sorry. Just a quick question about the clickers. I didn't have mine today. Does that count as a missed lecture?
No.
Okay.
You will send me an email.
Okay, I'm gonna send you an email. Thank you.